Here on the island, we are surrounded by the wonder of nature, full of beautiful flora. The natural splendour of this island habitat is remarkable. Interestingly, on our island, there is a large abundance of sycamore trees. We, the Phroggos, think it's really interesting how sycamore seeds travel from branches to all over the ground every May, seemingly with reckless abandon. Such we have chosen to look at how random this distribution of seeds is and how the weight of the seed influences the dispersal. Our hypothesis is that heavier seeds will be affected more by gravity and land in a more precisely concentrated spot.
Sycamore seeds, or helicopters, are samaras with a rigid membranous wing at one end. This wing typically has a slight pitch, like a propeller or fan blade, causing the seed to spin as it falls. Depending on the wind velocity and distance above the ground, helicopter seeds can be carried considerable distances away from the parent plant. The spinning action is similar to auto-rotation in helicopters, when a helicopter slowly descends after a power loss. The weight of the seed itself is enough to orient the whole structure, seed and helicopter wings. This is important because if the orientation changes, for example if the whole thing turns upside down, then the whole airflow around the structure will change and it will not auto-rotate anymore. The seed's rotation is caused by the extra drag from the wing part of the seed. This rotation causes tiny air vortexes, like miniature tornadoes, to form above the wing's leading edge. This lowers air pressure above the wing, sucking the body upward and creating lift. Although we could not artificially create this efficiency, thanks to our highly articulate model shown here, we were able to create a similar spinning pattern viable as a method of finding concentration density of seed dispersal.
Seed dispersal must be random for the plant to spread and survive successfully. Being spread about will reduce competition for nutrients, water and light between the growing sprouts, saplings and parent trees in the woodland. The sycamore, or Acer pseudoplantus, is the UK's most common maple tree despite not being a native species. This is likely because of the success of its travelling seeds, which manage to disperse more randomly and therefore find spots with the least competition. In our experiment, we will judge the most random set of data is one with the largest spread and most outliers, and we will hopefully be able to determine if heavier or lighter seeds do a better and more random job.
To fulfill our aim, the investigation of randomness in seed dispersal, we created a highly accurate model of sycamore seeds falling down a tree. In the initial phase, in which we thought of an appropriate representation of the seed, we came across these paper helicopters. Some initial testing showed that the fall of these replicas resembled the fall of the actual seeds. To create a difference in weight, we used differently sized paper clips. To mimic the height of the branch, we decided to release the paper helicopters from a high stairwell, at which bottom we would mark the center point right below the point where we were dropping the paper helicopters. While dropping it, we would make sure to always drop it from the same point to ensure reliable results. The distances to the center were measured with a piece of string, which was then measured with a 30-centimeter ruler. These additional steps made it more accurate than only using a 30-centimeter ruler straight away.
Our group, the Phroggos, were very aware of the dangers faced at each stage of this dramatic journey. Linus and I, running up and down those stairs, made sure to wear appropriate footwear and take our time, not rushing the experiment and getting the results we needed.
4 datasets were completed, with 20 results in each. This was a sufficient amount of data for analysis. I allowed for a measurement uncertainty of 0.5, as the ruler method is largely accurate. I chose to use a box and whisker diagram as it clearly shows the spread, outliers and anomalies in data. This is a quick explanation about the different parts of the diagram. As you can see, weight 1 has the largest spread of data, and this spread is inversely proportional to the weight. The number of anomalies and outliers also decreases as the weight increases. Therefore, I can accept our...
In conclusion, we successfully investigated randomness within seed dispersal. We proved that there is a correlation between weight and how random the spread of the seeds is. We all enjoyed this, as we think sycamore seeds are pretty cool. We designed this experiment and carried it out with consideration for all the variables, so it was as fair as possible with the materials we have. As a group, we worked really well together and each took responsibility for different parts of the investigation.
This experiment was reliable as we controlled all the variables well and had 20 data readings for each. It could further be improved by adding more data readings. However, the model for a sycamore seed wasn't completely accurate to a real seed as it had a long body. We could improve the experiment by using a more accurate model and loading it with a greater weight. The experiment could also be extended by accounting for the effect of wind on the randomness of seed dispersal through having a constant wind on the seeds when they drop.